Hello, students. In the previous lecture, we started solving systems, linear time invariant systems described by differential equation. That means the input-output relationship is described by differential equation. Today, we will have more examples on such kind of systems. So let's review. That means if I have an input x of t, and this is my system h of t, and this is linear time invariant system, and I have an output y of t. The relation between x of t and y of t is described by differential equation. This differential equation is from k0 to n ak. The k's derivative of y of t by dtk is equal to from k to 0 to m bk, the k's derivative of x of t by dtk. If I expand this means when k0, a0 y of t, when k1, a1 dy by dt, when k2, a2 second derivative of y of t by dt square plus and so on. And lastly, the nth derivative of y of t by dtn. And on the right side, the same, b naught x of t, b1 dx by dt, and lastly, bm dxm by dtm. Often n is greater than or equal to m, n is called the differential equation. If n is 1, first order system. If n is 2, second order system, and so on. Now, for example, application, where we have this application. For example, here, an application for solving electric circuit problems. Here, I have an input Vs of t, which is equal to x of t. This is called the source voltage. And I would like to find the output current, the current flowing through this series RLC circuit. This is a resistor, inductor, capacitor. So basically what I want to find the differential equation relating x of t, the input source voltage, and I of t, which is equal to yt, the output current. Now, what's the first step? The first step, we have to use the theory for circuit, okay? Solving electric circuit. Here, Kirchhoff's voltage law. What's Kirchhoff's voltage law? The sum of all voltage drops across the loop is equal to 0. So by using sign convention, for example, here from minus to plus is negative, from plus to minus positive. So this means minus Vs of t plus Vr of t, the voltage across the resistor, plus Vl of t, the voltage across the inductor, plus Vc of t, the voltage across the capacitor is equal to 0. Or Vs of t is equal to Vr of t plus Vl of t plus Vc of t. Now, Vr of t, R times the current, because it's a series circuit, R times I of t. And I of t is given by, it can be related to the capacitor voltage. I of t is C times the derivative of the voltage across the capacitor. Okay, and VL of t, L di by dt. Okay, and Vc of t is 1 over C, the integral, Vc of t, 1 over C, the integration of the current. Okay, now we substitute here. Okay, R I of t, L di by dt, and Vc of t is this one. Okay, then what kind of equation we have? We have this. Vs of t, Rit, plus L di by dt plus 1 over C, the integration of the current. This kind of equation we call integral differential equation because it has integration and differentiation, derivative. Now to make it pure derivative, differential equation, we can make one more derivative of both the left side and the right side. So the left side will be dvs by dt, the right side r times dy by dt plus L times the second derivative of y plus here the derivative of this integration will cancel. So derivative will cancel the integration, and I will have I of t. So 1 over c I of t. Now this equation becomes now pure differential equation because I have only derivative. Now Vs of t is x of t, the input voltage, I of t, y of t, the output current. So dx by dt, substitute these variables, input and output, dx by dt is equal to 1 over cy of t r times dy by dt plus L times second derivative of y by dt square. Now, if we see here, the order of the differential equation is second order. N is equal to 2, and A naught is 1 over 3, A1 are. How we find this S? We just look the coefficients for each term. If you see here the general equation, A naught means the coefficient of y. A1 means the coefficient of dy by dt. A2 means the coefficient of second derivative. It's actually very easy to memorize this because A1 corresponds to first derivative, A2 corresponds to second derivative, and so on. A3 corresponds to third derivative. And for B is also the same. B0, coefficient of x of t, B1, coefficient of dx by dt. And by comparing with the general form, we have A0, 1 over 3, A1 R, A2 L, B0, 0, B1, 1, M1, and 2. Now, when we find the solution of this, as we said last time, we have two ways. One way is to find the homogeneous solution, the particular solution, and then the complete will be homogeneous plus particular, and we solve for the constants of the homogeneous solution using the initial conditions. This is one way. The second alternative is find the natural response and the forced response, and the complete will be natural response plus forced response. In these examples, we just see the first alternative, which is we find the homogeneous and we find the particular, and we use the initial conditions to solve the constants of the homogeneous solution from the complete solution. Okay? Now, what are the initial conditions? If it is first order, I will have one initial condition, y at 0. Second order, two initial conditions, y at 0 and the derivative of y at 0. Third order, three initial conditions, y at 0, dy by dt at 0, and second derivative of y by dt at 0, and so on. Okay, continue like this. So the homogeneous solution, the particular and the complete will be yh of t plus y particular. Okay, and the homogeneous, we found it by solving this, and the solution for the homogeneous is this one, the general form. Summation from 1 to n c I e to the power of r I t, c1 e to the power of r1 t, c2 e to the power of r2 t plus lastly cn e to the power of r and t. R's, how we get? We will find them from the characteristic equation or the polynomial equation, which only depend on the s you see here, and it will be, for example, if it's second order, it will be like this: a0 plus a1r plus a2r squared is equal to 0. This is well known, and it is a quadratic equation. We have two roots. Now, if we have repeated roots, what will be the form? This form will be modified. For example, if I have a second order system with two roots, r1 is equal to r2, then yh of t will become c1 e to the power of r1t plus c2 times t e to the power of r1t. So this thing will be modified and multiplied by t, okay, because r1 is equal to r2, okay. If I have three roots, r1, r2 is equal to r3. They are repeated, So because they are identical, so I will have the first one, C1 e to the power of R1t. The second one, t times C2 t times e to the power of R1t. And the third one, C3 t square e to the power of R1t, like this. So it should be modified like this. Okay, now let's have example now. The example, this RC circuit. In this case, I take the RC circuit. This RC circuit have a source voltage, a resistance, and a capacitor. Okay, my output for this case is voltage across the capacitor. Vc of t is equal to y of t, and x of t, the input voltage. Let's find the relation between the output voltage across the capacitor and the input voltage. Okay, so Vs of t is equal to Vr of t plus Vc of t. Vr of t, R times I of t, C dVc by dt. Vr of t, R times I of t, so R times C dVc by dt. So Vs of t, Vr of t plus Vc of t. So Vr of t is R times C dVc by dt plus Vc of t. Now we have Vs of t and Vc of t. Vs of t is the input, we call it X of t. Vc of t is output voltage across the capacitor, we call it Y of t. So I have this differential equation. Now when you see this differential equation, what's the order? It's very clear, it's first order, because the maximum derivative I have in this equation is first derivative. Okay, I do not have second derivative. So n is equal to 1. M, no derivative for x, so it is 0. P0, the coefficient of x, 1. A1, the coefficient of dy by dt, r times c. A0, the coefficient of y of t, which is a0. Then the homogeneous, I will have definitely one root, so it will have, this is a general form, from 1 to n c I e raised to r I t. So from 1 to 1, it will be C1 e to the power of R1t. The polynomial equation, I have this from k0 until my n is 1. Okay, ak r power of k is equal to 0. If I expand, this is a compact form. If I expand this, I have a0 plus a1r is equal to 0. A0 is 1. A1 is r, capital R times c. Okay, don't mix it, confuse it with small r. Small r is our variable. R, capital R is known, it is a resistance. 1 plus r times c, small r is equal to 0. So small r will become negative 1 over rc. Therefore, the homogeneous solution is C1 e to the power of R1t, C1 e to the power of negative 1 over rc. Now we find the homogeneous. The particular solution will have the same form like the input. What does it mean? For example, if suppose the input is a constant 1, the particular will be constant also. Y, P of t constant. Suppose the input is unit step, the particular will be Cp times ut, and we need to find Cp. Suppose the input is e to the power of at, the particular Cp e to the power of at. And if it's e to the power of at ut, Cp e to the power of at ut. And we need to find Cp. If it is cosine and sine, I will have Cp1 cos omega naught t, Cp2 sine omega naught t, and I need to find Cp1 and Cp2. Now, let's have this same circuit now, and let's say the input is cosine omega naught t. Okay, general now, and let's find the particular solution. Okay, so the particular is Cp1 cos omega naught t plus Cp2 sine omega naught t. We need to find Cp1 and Cp2. How? By substituting the particular solution in the differential equation. The original differential equation is, if we substitute it, we have yp of t rc dyp by dt is equal to xt. So what's the derivative of this, the particular solution? The derivative of this plus the derivative of this. The derivative of the first part is the derivative of cosine is minus sine, and by chain rule, the derivative of omega naught t is omega naught, so it will be minus cp1 omega naught sine omega naught t. Second part, the derivative of sine omega naught is cosine omega naught t, and by chain rule, the derivative of omega naught t is omega naught, so cp2 omega naught cos omega naught t. So we substitute here. This is the derivative. You should multiply by r times c. Okay, then yp is the original yp is this one. Okay, and rc times the derivative of yp, we multiply this by rc, and we'll have this one and this one is equal to x of t cos omega naught t. After we do this, what we should do? We should group similar terms. So here I have cosine, and here I have cosine. Combine these two, common cosine omega naught t. So this will be cos omega naught t common cp1 rc omega naught times cp2, one coefficient, and we group the sine together. Sine omega naught t is common cp2 minus rc omega naught cp1 is equal to cos omega naught t. Now the left overall equation is equal to the right equation. So in order the two to be equal, okay, the coefficient for the cosine, because the coefficient for the cosine, the right side is 1. So the coefficient for the cosine part for the left side should be equals to 1. The coefficient for the sine should be 0 because I do not have sine on the right side. So cp2 minus rc omega naught cp1 is equal to 0. From this cp2, from the second, cp2 is rc omega naught cp1, substitute in the first for cp2. Then we'll simplify, and after simplify, we get cp1, and then we get cp2. I have two equations with two unknowns, cp1 and cp2. RC and omega naught, these are known from the circuit. So I get cp1 and cp2. Therefore, the particular is given by this equation. Now, find the complete solution of this example. Again, given R is equal to 1 ohm, C is equal to 1 farad, and the initial condition Y at 0 is 2 volt. Why we need the initial condition? Because when we write the complete solution, remember from the homogeneous part, I will have C1 constant, which is not yet known. So yc of t, the complete solution, is yh of t plus y particular of t. That means the homogeneous part, this one, plus the particular, which I found it here. So combine these two. And let's say to simplify the equation, like we substitute R1 ohm, C1 farad omega naught is equal to 1. Then I have a simplified equation, y complete is C1 e to the power of minus t plus half cos t plus half sine t for t greater than 0. Now, what is unknown? Unknown is C1. So from this, the initial condition is already given. The initial condition, y at 0, the capacitor voltage is equal to 2. So C1 plus half cosine of 0 is 1, sine of 0 is 0. C1 plus half is equal to 2. C1 2 minus half is equal to 3 over 2. Then I have the complete solution given by this. Okay, so to summarize, we found the homogeneous solution and we find the particular solution. We add the two and we solve the constant from the homogeneous solution. Okay, we determine the constant from the homogeneous solution using the initial condition. Okay, that's all the steps. Now let's do one more example here. Solve this differential equation. Find the output yt given the differential equation this. Remember, this differential equation, it can be for any mechanical system, electrical system, or chemical processing system, any process. So it can be described by the differential equation. And of course, it will have its own parameters depending on the elements for that system. For example, for our electric circuit case, the elements are resistors, capacitors, inductors, and so on. Okay, so already I have here those S constant numbers. Okay, so the input is x of t e to the power of minus tut, because what's the order? This second order. So I will have two initial conditions. Y at 0 minus half, the derivative of y at 0 half. Okay, so basically what these three things should be given to solve the differential equation. So find the output yt. Solution, the first step, the order to determine the A's and the B's. A0, 6, coefficient of y. A1, 5, coefficient of dy by dt. A2, 1, the coefficient of second derivative, because this is 1, the coefficient. B0, 1, the coefficient of x of t. M0, no derivative for the x of t. Okay, so second order system. Homogeneous, the general form from the summation from I equal to 1 to n c I e to the power of rit. So from 1 to 2, c1 e to the power of r1t plus c2 e to the power of r2t. So this is provided r1 and r2 are different. If they are repeated, we need to modify the second part as we discussed before. So let's substitute now. A naught is 6, r power of 0 is 1, a1 5r plus r square is equal to 0, r square plus 5r plus 6 is equal to 0. This is, you know it very well, this is quadratic equation, and we need to find two numbers whose sum is 5, product 6, they are 2 and 3, so r plus 3 times r plus 2 is equal to 0 when we factorize this equation. Then r1 minus 3, r2 minus 2. Then the homogeneous solution will become yh of t c1 e to the power of minus 3t plus c2 e to the power of minus 2t. The particular solution. The particular solution will have the form of cp e to the power of minus tut. Why? Because remember, the particular solution will have the same form like the input. So if the input is x of t e raised to minus tut, then the particular solution will be Cp e raised to minus tut. So we substitute in the differential equation yp. So the second derivative of yp of t plus 5 dyp by dt plus 6 yp of t is equal to xt. So we need the first derivative of yp and the second derivative of yp of t. The first derivative, because this exponential, it is easy. What's the derivative of cp e raised to minus t? It will be minus of cp e raised to minus t for t greater than 0. And if the second derivative, do one more derivative, then it will be, this negative will be positive, cp e raised to minus t, which is the original actually, y of p of t. So the second derivative is this. Then substitute in the equation. Okay, the equation is the second derivative plus 5 times the first derivative. So minus 5 times cp raised to minus t plus 6 times yp, 6 times cp raised to minus is equal to x of t e raised to minus t. Then add this, all this, when you add this, it will be 2 times cp e raised to minus t is equal to e raised to minus t. The left equation should be the right. From this, cp is equal to half. Okay, so we got the particular solution half e raised to minus tut. Okay, therefore now the complete solution, the homogeneous plus the particular. The homogeneous, if you remember from the two roots, I have c1 e raised to minus t 3t plus c2 e raised to minus 2t plus the particular half e raised to minus t. This is a complete. Now, are we done? No, not yet, because we need to solve C1 and C2. From where? From the initial condition. We have two initial conditions, y at 0, the complete solution at 0, and the derivative of the complete solution at 0. So I need the derivative of the complete solution. What's the derivative of this? The derivative of the first is minus 3 c1 e raised to minus t. The derivative of the second, minus 2 c2 e raised to minus t, minus the derivative of this is minus half e raised to minus t. Okay, so the first initial condition is negative half. I go back here to see y at 0, negative half, and the derivative of y at 0, positive half. So y at 0 means substitute t is equal to 0 here in the complete solution. C1 e to the power of 0 plus C2 e to the power of 0 plus half is equal to negative half. So C1 plus C2 is equal to negative 1. And when half goes there, negative 1. And the derivative of y at 0 means here minus 3 C1 minus 2 C2, because this is e power of 0. E power of 0 is 1. So minus 3 C1 minus 2 C2 minus half is equal to half. When half goes to the right, minus 3 C1 minus 2 C2 is equal to 1. Now I have two equations. The first one, this one, C1 plus C2 is equal to negative 1. And the second one, minus 3C1 minus 2C2 is equal to 1. This is negative 1. The first is equal to 1. The second. So simultaneous equation, two equations with two unknowns. You can solve it by substitution and variable elimination. Or here, to eliminate, for example, here, what did I do? I eliminated C2, so I multiply the first by 2. So this will be 2C1, 2C2 is equal to negative 2, and I added with the second. So when you add this, it will be minus C1, C2 will cancel, is equal to negative 1, C1 is equal to 1, and from the first one, C2 is negative 1 minus C1, negative 1 minus 1 minus 2. So I found C1 and C2. Therefore, the complete is C1 is equal to 1 e raised to minus 3t. C2 minus 2, C2 is negative 2, minus 2 e raised to minus 2t, plus half e raised to minus t, for t greater than 0, which will be this one. Okay, so I hope you understand the examples for solving differential equation or systems described by linear constant coefficient differential equation. As we said, this differential equation can be used to describe a system. For example, it can be electrical system, mechanical system, any processing, manufacturing system, any control system described by differential equation. And the idea is given, the objective is given the input and the initial condition, and to determine the required is to determine the output y of t. So we can solve this by following the procedures as we discussed. Please redo the examples and also solve the exercise problems. If you have any questions, you can always ask me or write me an email. With this, we finish the solving differential equation, and thank you for listening to this lecture.